So we took a really long time with 10.4, and the reason being is because we're setting up a structure here that's going to kind of be consistent through the rest of the course. I don't mean the chapter, I mean the course. And you can see here, this is the first page of the notes for 10.3, which is our next section, that a lot of it looks very similar. You still got 6 steps, you still got this giant table, which I would totally print out and use. Now, the thing about this is that this is for the mean now. This is not going to be for proportions. So since it's the mean, just like in chapter 9, you don't know sigma, so you're stuck with using something called the t-distribution. So this is called a t-test. Now, you still have to have simple random sampling and unbiased and independent and all of that good stuff. If you don't have those things, you've got bigger problems that you have to deal with. But for this section, we need a much smaller n. I mean, you can have a really large n, that's fine. But here you need n to be greater than or equal to 30. And again, that's based on the central limit theorem from chapter 8.1. Whereas back in 10.4, you needed, you needed n times p times 1 minus p to be greater than 10, which in general means much larger than 30. I mean, this is for proportions. This is stuff like surveys and samples. So like President Obama's approval rating or whatever. Whereas down here, we're talking about the average. Like, what's the average body temperature for all people on the planet? That kind of thing. All right, now notice there are the hypotheses, very similar to before, but these are with mu now and not p, because we're dealing with the mean here, not proportions. Then level of significance is alpha still. Test statistic, there's the formula for it. Not nearly as involved as the other one. Then you have your pictures, which work very similarly to the old ones. This is for classical, this is for p-value, but they're very similar. They're just with t's instead of z's. And then same as with your rejection and then your conclusion. All right, so let's look at it. According to the U.S. Mint, quarters weigh 5.72 grams. A researcher is interested in determining whether the new state quarters have a weight that is different than the old value of 5.72 grams. He randomly selects 18 state quarters, weighs them, and obtains the following data. So there he is. He gets 18 random quarters. So is it possible to conduct a hypothesis test for this data? Okay, well, first of all, we know that it was data was from a random sample. We assume independent as well, right? Reason being, because it was a random sample, you assume that just because you have quarters of one weight in your pocket doesn't mean that it's affecting the weight of the other quarters, if that makes sense. Now, why are they giving you these pictures? Well, the graphs are given because n is less than 30, and we weren't informed that the data was normally distributed. So the graphs show us that the data is normal with no outliers. Therefore, we can conduct a hypothesis test. Okay, so you need to know that the data is normal with no outliers. If it's not given to you, that's okay as long as your sample size is greater than 30. But here, it's not given to you and your sample size is less than 30. So those two things kind of combo to make a 1-2 punch of badness. So what you got to do is you have to get a normal probability plot and a box plot to prove to yourself that, hey, this sample came from a population that's normal. That's what that graph shows, with no outliers. That's what that graph shows. And because it is, then we're okay for making a hypothesis test. If they didn't give us these graphs, we would have to have a sample size greater than 30 here, or we would have to be told somewhere up here that it was normal. Right? We weren't told either one of those things, so we have to see the graphs to prove it. All right, done with that. Next, can we run this test? Well, we can run it, so let's run it. Step 1. You still need to make your hypotheses. Poof, there we go. All right, so we assume that it's 5.72, because that's what it used to be. And then they say, is there evidence to prove that it's not 5.72 anymore, different than 5.72? So that's a two-tailed test. See right there, different. Then they gave us alpha, which was 0.05, right there. All right, step 3, we're going to have to find this test statistic. But I don't think we're going to have time to do that in this particular one. Let me type it up. All right, poof, there it is. We can talk about where this came from in the next one and how this turns out in the next video. I'll see you then.